Yeah, welcome to my talk, Monitoring Climate Change, with a focus on machine learning, how machine learning can improve climate models, projections, and technology assessments. It's a huge pleasure to speak at this very important conference, so thanks very much for the invitation. I'm going to introduce you into this topic by starting with the current state of climate change based on the Intergovernmental Panel on Climate Change Assessment Report, Working Group 1, that was published last August, where I have been a coordinating lead author of the chapter Human Influence on the Climate System. And in this report, we made some very strong conclusions on the state of the current climate system. Like, it is unequivocal that human activities are causing climate change. But nevertheless, there are some uncertainties that I will introduce you to where we can make stronger assessments, in particular for improved technology assessments and for actionable climate science. And here is where I get in part 2 to how we can use machine learning to improve upon where we are at the moment. And that opens also collaboration possibilities with industry, and that is obviously also very relevant when I get to my third topic of the talk, which is limiting climate change, where I will introduce you to remaining carbon budgets, are we on track, and what are the challenges. So let me start with the current state of climate change. We can observe CO2 atmospheric concentration that you see in this figure here since many, many decades. So you see that the CO2 concentration has risen from around 280 ppm, parts per million, in the pre-industrial area, which is often like measured in 1850, over time, and you can see that it's continuously rising. So no change, we are on the path, we are still CO2 concentration in the atmosphere is increasing. We are now at 420.99 as this NOAA measurement shows. And we also know that when we emit CO2 into the atmosphere, accordingly, the temperature is rising. And the IPCC AR6 Working Group 1 report concluded that we are around 1.1 degrees above pre-industrial times already. So that's pretty close to the 1.5 degree temperature goal. And we also observe that each of the last 4 decades has been successively warmer than any decades that preceded it since 1850. So there is still a climbing up in temperature and no change. So one of our tasks as climate scientists is then to see, why is this? So we want to know, is this due to human activity, or is this maybe just something that occurs naturally? And for this, we are using climate models, and I get back to climate models in part 2. And actually, the IPCC assessment report already in 1995 pointed to this. That was actually the reason why I entered climate science, because I was very interested in this, so I did my PhD here. But over time, the evidence has strengthened, and now we could conclude that it's really unequivocal that human influence has warmed the atmosphere, ocean, and land. And how do we do this? Why are we so certain? And that's where the climate models come in. So basically, when you have a climate model, you run this with forcings like CO2 emissions or concentrations, as I have just shown you. So you step this model forward in time, and then it calculates the climate response. And you see here in the black curve, we use observations. So we observe the climbing up of the global mean temperature, and then we do simulations with our climate models where we include all forcings like CO2, other anthropogenic forcings, and the natural forcings, which are solar variability and volcanoes. And then so you see that this brown curve here quite nicely matches the observations, and then we take out the anthropogenic forcings and run simulations just with solar and volcanic, and you can see that by no means this temperature increase can be simulated. And that makes us very strong assessment, like it's unequivocal. And likewise, the report concluded that climate change is already affecting every inhabited region across the globe. And we could also say that here human influence was contributing to many of the observed changes in weather and climate extremes. So we have had this in Germany as well, and there are many other examples around the world which demonstrate that unfortunately this human-induced climate change is real. Now, this was a brief run over like the current state of climate, where are we now? And a very important task for us as climate modelers is that we project the future. So what's going to happen in the future? And the way we do this is we run different scenarios. So we as climate modelers, we don't say this and that is going to happen, because that's a world decision on which path we are going in terms of CO2. But you can see here the 5 scenarios that we were running with our climate models in terms of carbon dioxide emissions. And the lowest one, the 2 lowest one in blue are low scenarios where the CO2 emission pathway is actually declines immediately and gets towards net zero around 2050 or 2070 in the low. Then we have 2 high scenarios where CO2 continues to climb on current rates or slightly reduced rates. And here you see that CO2 continues, the annual emissions continue to rise in the high ones. And we have one intermediate scenario. So we put these basically into our climate models, and then we look at the response. And that's what we get in terms of global surface temperature change. You see again the 2 blue scenarios, which are the lowest scenarios. And on the x-axis here, you see the temperature increase be above pre-industrial levels. And you can see that for this, we only get towards 1.5 degrees Celsius if we really comply to the low scenarios that I have just shown. And that makes a pretty strong statement, because, and that is a very strong statement of the IPCC Working Group 1 report, is that unless there are immediate, rapid and large-scale reductions in greenhouse gas emissions, limiting warming to 1.5 degrees and even 2 degrees will be beyond reach. And I just go one back again. Look at this. It means that in just the blue curves are the paths where we can reach these temperature goals. It means immediate action, and it also means net zero towards 2050, very latest. And so basically this is the projection in terms of global mean temperatures, but it also propagates into extreme events. So we could also show that if we continue on passes like 1.5 degree, 2 or 4 degrees, the likelihood of extreme events will be increasing with the global warming level we reach. So that's the world we have in front of us. That's the world we have to choose. And I have shown you what is required here, and I will get back to this briefly in part 3 when I talk about limiting climate change. Now, these were very strong conclusions. It's not that they are disputable. Nevertheless, we have some uncertainties here, and that's where machine learning come in. So that's a big part of my research, actually since 5 years. We are using machine learning to improve climate models and projections. And I will introduce you to these concepts and also to the motivation why we are doing this, and possible collaboration with industry in this second part of my talk. So what is a climate model? A climate model is one of the most sophisticated approaches we can choose to simulate the climate system. It's based on 3D computational models that are based on fundamental laws on physics, and that's why we believe these projections. So conservation law of energy, momentum, mass. And then what we need to do with like every numerical model, we need to discretize, and that's what the plot you see in the middle. So basically, we partition the atmosphere and the ocean into these grid boxes you see here in the middle panel. And then for each of these grid boxes, we solve the so-called primitive equations that that will step forward. We step forward in time. Let's say you step forward, you double CO2 concentration. How is your response in the climate system in each of these grid boxes for the key variables like temperature, precipitation, pressure, and so on. And then we also have some physics in there, which we need to simulate. And more broadly, then the way we do the projections is that basically climate modeling groups around the whole world are running or developing and running specific simulations. We are coordinating as part of the Coupled Model Intercomparison Project CMIP that I chaired over this last round. So you get model simulations, for example, the historical and the projections from 40 to 60 model groups, and then you lump them together, and that's your projections. That's the one I have shown before. And one important task that we need to answer is, well, are our models any good? And the only way how we can compare, how we can trust them, because they're based on physical laws, but we also need to have a reality check here, and that's where we compare them to observations. That's a pretty difficult figure. I don't want to go in details. It basically shows for each of the different generations of CMIP. So CMIP 6 was like 40 models supporting APCC AI6 in 2021. CMIP 5 supported the previous one in 2013, and CMIP 3 the next previous one. So in green you see green, blue, red. You see this for different variables that are important for climate, like radiation, precipitation, surface. And basically what it shows is the model's climatology as a 2D plot compared to an observation. And we could show with this figure that indeed these models are improving, and they are very good in reproducing large-scale indicators of climate change. So is this good enough? Not really. And that's where we really need to improve upon what we have at the moment to allow reliable technology assessment and actionable climate science in particular, because our projections need to become more regional. And one of the key uncertainties I show you here in this figure is the climate sensitivity, which is a metric when you double atmospheric CO2 concentration. What is the response in global mean temperature? And the blue bars show you the range, which is around 1.5 to 4.5 degrees. And that's a pretty awkward large range for a quantity like this. You really don't want this. And it propagates directly into our global mean temperature projections, into precipitation and so on. So really, I mean, I was seeing this 5 years ago, and I really wanted to improve this. So there are basically a few big moves in climate science or modeling that try to overcome this issue. So why is this? Why do we have this problem overall in the first place? It's because I showed you about these grid boxes, and they are like 100 kilometers, kind of. So when you look outside and you see a cloud, you know it's not going to form on a 100-kilometer scale. It's forming on a much lower scale, like meters or kilometers. So what we need to do in these models is that we need to represent these subgrid scale processes in terms of statistical parameterizations based on some physical laws, but also parameters. And that really made us stuck, because like the one model responds differently than the other ones, and it's hard to constrain. And that's similar true to for other processes like the carbon cycle. So our approach is now taking opportunity of the huge computer power that's out there, that has become available over the last years. And what we do is basically we combine the massive data from observation. Another move is that you could think about just run it on higher resolution, and that's what one big effort is now in climate modeling. You just run it on, let's say, 5 kilometers. But the problem here is that you can't run these simulations very long. They are extremely expensive and have huge outputs, but we can learn from them. We take short, high-resolution cloud-resolving models that are available, let's say, for a few days or maybe 2 years. And for fast processes like clouds, we take them to learn, and we take the progress in machine learning to build a coupled hybrid model. How do we do this? So please initially just look at the upper slide. So on the left-hand side, you see this high-resolution data a video. So it runs, it's let's say 5 kilometers or even lower. And what we do is we coarse grain these inputs, and for the state variables, but also for the tendencies. So the tendencies are like the change in temperature due to a formation of a cloud, for example. And then we train a neural net, and the idea is that in the end we will throw out we will remove the physical parameterization, and we will bring back our machine learning parameterization in the hope to have a better cloud. And with this, we are hoping to bridge across the high-resolution effort, which is really important to simulate these processes exactly. But we will also continue to need low-resolution Earth system models that include other processes like permafrost and carbon cycle, and that we will not be able to run on this very high resolution for the next decades. So this is the bridge, and we actually got quite successful in our first work where we included a cloud cover parameterization. So the general approach here is the general approach is that for these physical parameterizations, as I just explained, we are using our machine learning approach in order to improve the climate model and hopefully give more reliable projections also on the regional scale. And then we want to accelerate the dynamical core with some other approaches. And overall, we are hoping that this will alleviate many biases. It will reduce uncertainty. It will also allow to run larger ensembles, which is very important in particular for extreme event attribution. So we are now faced with an extreme event comes. Now we need to say, is it anthropogenically forced, or is it maybe just natural variability? And that's where we, among other things, need large ensembles. But the machine learning activity also provides great opportunities to collaborate with industry, and I think that's something where which was discussed, for example, at the panel yesterday, where like academia and industry need to increase collaboration and transfer. And here, in particular, I would like to name deep learning and causality, but also quantum computing and quantum machine learning, as well as the development of digital twin Earth that is basically allows the user to interact with data and simulations to extract information. So it basically revises the order of how we do climate science now, and it would be an extremely advanced decision support system for a step change in fidelity of climate information, where a lot of companies are now starting to collaborate with academia. Okay, because we are here for at this great conference, obviously an collaboration opportunity is in terms of limiting climate change. And so why is this so important to reduce CO2? I have shown you these scenarios initially already, but this is basically the reason why why every ton of CO2 we emit today really should be avoided. And that is because we have a nearly linear correlation between the cumulative CO2 emissions. So these are all CO2 emissions we have been emitting up to date, and the increase in temperature. And what does this mean? So it basically means that reaching net zero anthropogenic CO2 emissions is a requirement to stabilize human-induced global temperature increase at any level. And it also means that if we want to reach a certain temperature, then we only have a limited carbon budget left. And this is what is left for us. So I'm now going to talk a few slides about are we on track? So first of all, this is a paper from my colleague Pierre Friedenstein from this year about the carbon budget. So we have these are concrete numbers. Of course, they are associated with uncertainty levels. But in order to reach the 1.5 degree goal, we have around 420 gigatons CO2 left, and in order to reach the 2 degree goal, we have around 1,270 gigatons per CO2 left. And when you look at the annual anthropogenic CO2 emissions that were given as 40 gigatons CO2 per year for 2021 in this paper, then really you see that reaching zero CO2 emissions is a huge task. Okay. Haven't seen that. Okay, this slide is also quite important because that basically says, are we on track? And it shows that with current policies, we're not on track. And even with the pledges that have been put in for the COP26, we are not. So in order to reach 1.5 degrees, we really need to reduce CO2 emissions immediately and halve them by 2030. And but there is also evidence of climate action and a glimpse of hope. So new renewable energies have been introduced, and this is a figure from the Working Group 3 report, and you see that the costs have been decreasing for renewable energies, and at the same time the use has scaled up, and this creates new economic opportunities, and likewise there are options available now in every sector that can at least halve emissions by 2030. And here are just a few examples. Prominently, of course, the energy sector, but also transport and industry and all these other sectors that are listed here. At DLR, we also work on contributing to reach the 1.5 temperature goal. We are working in the area of digitalization, as I've shown, but also monitoring the air system, monitoring political agreements, and a big part in aeronautics, transport, and energy, where we develop an assessment and mitigation options to reduce climate impacts with alternative fuels or technology development and contributions to the energy transition. And also, we are working on the technology and knowledge transfer to industry, politics, and society, which we all learned and know is really important. So let me conclude in terms of the first part, the current climate change. We know it's unequivocal that human influence has warmed the atmosphere. We are around 1.1 already. Each small increase in warming leads to more severe climate change impact. So that's also a very important statement. It's not, we shouldn't divide the world into this 1.5 and 2. Basically, every warming that we can avoid is important. And we can only reach 1.5 and 2 degrees if we really have deep reductions in CO2 and other greenhouse gases to avoid very, very dangerous climate warming. Machine learning can help here. I showed that. It has a great potential for improved technology assessment and actionable climate sciences, also in collaboration with industry. I haven't talked about the challenges this topic brings along in terms of generalization and explainability and so on. Happy to talk about this in the break. And in terms of limiting climate change, I showed that the pledges are not sufficient. We really need critical steps and shifts in economies and technologies to reach this net zero emissions. We have some positive developments in terms of renewable energies costs and use. So they scale also, which is important for the market. And this really creates new economic opportunities. And now is really the time for investments in these to scale up low carbon electricity and to reduce emissions from industry and all other sectors. So I conclude with IPCC, the assessment report. We had 3 working groups, has really provided a reality check, and the evidence is clear. The time for action is now, and I count on you, Climate Tech. Thank you.
Thank you so much, Veronika, for this great talk. Are there any questions?
You taught here.
Yes, warming climate on the stage
yeah.
too. There's a question. You get a mic.
Oh, okay. Thank you. So you showed that climate models have continuously improved. So is there any systematic direction if, like, in the past, the predictions were always too low or too high? And is this incorporated in some way?
Yeah, so I mean, a big debate was this climate sensitivity that I showed, that some of these models showed a very high response to doubling of CO2. And that was actually also in the press quite a bit. And there were a lot of efforts to try to reduce the this climate sensitivity or to constrain it. And in fact, the conclusion was that the high climate sensitivity models, you have a larger response in temperature, but it is also important to look at these in terms of the distribution and the tails, because it's not, I showed very much just the mean, but the tails and the extreme events will become important. And the other way that was done was that many of the projections you will see in the IPCC report are climate warming levels, and then these uncertainties get basically removed from this assessment. So in terms of this, there is improvement, and the effort I have shown is exactly to try to make the climate models more sensitive in this regard, better in this regard, because the reason why this huge spread in the climate sensitivity is indeed because of the subgrid scale processes and the clouds. So there are these two basically efforts: the high resolution, you just resolve the cloud, but you know, you can't do this for very long. And our machine learning approaches that bridge. And I think with these two, we will have the chance to provide more exact and more regional projections, while not saying that anything we said in this round was not on solid grounds, because it was, we spent years on this report. And so I truly stand behind all of these statements, despite the uncertainties we have.
Thank you. One more question, maybe. Okay, two. We start here. Sorry.
Yes. Can you say some words on the current state of this Digital Twin of the Earth initiative?
Yeah, so I think that's only starting. The digital twin is a complete new concept. I should say that what I showed here is I coordinated this huge activity, the CMIP, when we collect all the output, and we first do the forcings, we run the climate models, and then we do all these analysis. And the digital twin tries to reverse this, so make it more user-friendly. And there are first attempts to do this, and industry is also, or some companies are investing in this. It makes use of the technology development. It is a long path, so I would say it's in the early stages. And the goal is to have an interactivity, that it can be used as a supporting tool. On the other hand, it will also have to consider it cannot be just built on high resolution models, because there are other processes like carbon cycle and permafrost, and the uncertainty needs to be somehow also visible, because when you make a decision, you also want to have the uncertainty that comes along with it.
One short question and a short answer.
Okay.
You've shown this quite well, this large spread of the temperature. What do you think what is possible in terms of getting to a more accurate model in the future, and when would that be possible?
Yeah, I think it will be exactly this combination. I showed high resolution and machine learning and further development of the coarse scale Earth system models that has huge potential, actually, I would say. So I think we will be able to reduce this uncertainty by the next assessment report.
Great. So we stop here with a positive message. Thank you so much. Thank you for your questions. Thanks. Warm applause for Veronika, please.